We see structures all around us, from towering skyscrapers to elegant bridges. But what exactly defines a structure in engineering terms? Simply put, a structure is any assembly of materials designed to sustain loads and resist forces. Think of a simple chair. It's designed to support the weight of a person, resisting the force exerted by their body. The legs, seat, and back all work together, transferring the load to the ground. Structures come in all shapes and sizes, serving a myriad of purposes. Buildings provide shelter, bridges connect communities, and dams harness the power of water. Each structure is carefully designed to withstand the specific forces it will encounter, whether it be the weight of snow on a roof or the wind load on a skyscraper. Understanding the fundamental principles of structural behavior is crucial for engineers. They need to analyze how forces are distributed throughout a structure, identifying areas of stress and strain. This knowledge allows them to select appropriate materials and design efficient, safe, and aesthetically pleasing structures that meet the needs of society. Structural design is a captivating blend of art and science. It involves transforming creative visions into tangible realities while adhering to the fundamental principles of physics and engineering. Imagine the iconic Sydney Opera House, its soaring shells a testament to the power of imaginative design. The design process begins with identifying the purpose of the structure and the loads it must carry. This could be anything from the weight of people and furniture in a building to the dynamic forces of traffic on a bridge. Engineers then use their knowledge of materials, structural analysis, and computer modeling to develop a design that meets these requirements. Creativity thrives within these constraints. Engineers explore innovative forms, experiment with new materials, and optimize structural systems for efficiency and elegance. The result is a harmonious balance between aesthetics, functionality, and safety. While the fundamental principles of structural design remain constant, designing civil structures differs significantly from designing mechanical products. Civil structures, such as buildings and bridges, are typically large-scale, static structures designed for long service lives. They must withstand environmental loads like wind, snow, and earthquakes, often over centuries. Mechanical products, on the other hand, are often smaller in scale and may involve moving parts. Think of an airplane wing or a robotic arm. These designs must account for dynamic loads, fatigue, and vibrations. This difference in scale and functionality influences the choice of materials, design methods, and safety factors. Civil engineers often work with concrete and steel, while mechanical engineers might utilize lighter weight materials like aluminum or composites. The design process for both disciplines requires rigorous analysis and testing to ensure safety and reliability. Section 4. Analyzing for success, stress, strain, and beyond. Analysis forms the backbone of structural design. Before a single brick is laid or a beam is bolted, engineers meticulously analyze the proposed structure to ensure its stability and safety. This involves applying the principles of mechanics to determine the internal forces, stresses, and deformations within the structure under various loading conditions. Sophisticated software tools like finite element analysis, or FEA, allow engineers to create complex computer models that simulate real-world conditions. These models help visualize how the structure will behave under load, identify potential weak points, and optimize the design for efficiency and safety. Analysis is an iterative process, with engineers refining the design based on the analysis results. This ensures that the final structure can withstand the anticipated loads with an appropriate margin of safety. Section 5. Permissible stress versus Limit State 2. Design philosophies. Two main philosophies govern structural design: permissible stress design and limit state design. Permissible stress design, also known as allowable stress design, is a more traditional approach. It relies on limiting the maximum stress experienced by any part of the structure to a predetermined allowable stress. Imagine designing a steel beam. In permissible stress design, you would calculate the maximum stress the beam would experience under the expected load. This stress would then be compared to the allowable stress for the specific grade of steel being used. If the calculated stress is lower than the allowable stress, the design is considered safe. Limit state design, on the other hand, is a more modern approach that considers multiple failure modes. It aims to ensure that the structure does not reach any of its limit states, such as collapse, excessive deflection, or fatigue failure, under the anticipated loads. This approach allows for a more nuanced understanding of structural behavior and often results in more efficient designs. Both philosophies prioritize safety and reliability, but limit-state design is gaining increasing acceptance due to its comprehensive approach. Section 6, the Golden Gate, where creativity meets safety. The Golden Gate Bridge stands as a testament to the harmonious marriage of creativity and safety in structural design. Its iconic orange towers, soaring 746 feet above the water, are not just aesthetically pleasing, but also a marvel of engineering ingenuity. The bridge's design, a suspension bridge, was chosen for its ability to span the vast Golden Gate Strait. The design team, led by engineer Joseph Strauss, faced numerous challenges, from strong currents and unpredictable winds to the potential for earthquakes. They incorporated innovative features such as the bridge's flexible roadway, which can move laterally up to 27 feet to accommodate wind and temperature changes. The Golden Gate Bridge is a powerful reminder that safety and aesthetics are not mutually exclusive. Innovative engineering solutions can be both functional and beautiful, pushing the boundaries of structural design.